Okay, I'm going to warn you as I'm making this video, if you hear a slight crunching noise, it's my dog chewing on her bone, so don't mind her. So we're going to start the second derivative test for relative extrema. Remember before we talked about the first derivative test, and if it changed from positive to negative, there's a relative maximum there, or if it changes from negative to positive, there's a relative minimum there. This is a different case. This time, if we find a critical value, and the second derivative is positive, then it's a relative minimum. And so that's going to be because if it's concave up like a cup, there's going to be a minimum value there. Okay, if it's concave down like a frown, there's going to be a relative maximum. If the second derivative equals 0, then the test fails and you got to use the other one. So with example 6, we're going to find the relative extrema 2 different ways and justify it using both of our rules that we already know. Just to get an idea, we do know that this function is a quintic function. All right, it's going to be something like this. We're not exactly sure on the specifics, but maybe we can get a better idea by analyzing it a little bit. So we have the first derivative, negative 15x to the 5th plus 15x squared. Let's find our critical values. It's not going to be undefined. So if I take out a negative 15x squared, I end up with x squared minus 1. So we have critical values at x equals 0, x equals 1, and x equals negative 1. So using our first derivative test, we're going to plug in those values to our first derivative. Let's see, maybe negative 2, negative 1/2, 1/2, and 2. You should get negative, positive, positive, and negative when you plug those in. So by the first derivative test, f has a relative max at x equals 1, since the first derivative changes from positive to negative, and f has a relative min at x equals negative 1, since f prime changes from negative to positive. So that's justifying it using the first derivative test. Let's look at now the second derivative test. We would take the second derivative, so we get negative 60x cubed plus 30x. All right, let's plug in negative 1, our critical values. If we plug in negative 1, we're going to get a positive value. If we plug in 1, we're going to get a negative value. And if we plug in 0, our other critical value, we're going to get 0. So by the second derivative test, it tells us that f has a relative min at x equals negative 1, since f double prime of negative 1 is positive, and f has a relative max at x equals 1, since f double prime of 1 was negative. So there you go. One might be more useful than the other if the second derivative is easy to analyze. If the second derivative is difficult to find, then you're probably not going to use the second derivative test. Example 7 has a lot going on. We have a lot to look at. We're going to do 7b together, and I would like you to do 7 or 2, and you're going to do 7-1 on your own, and you can put some of your answers to your wish. Don't put all of them. There are way too many. Just put the answers to, let's say, C and E. How about that? All right, so there's a lot. All right, where is f increasing or decreasing? Now, keep in mind, this is the graph of the derivative. F is increasing when the derivative is positive. So we have f is increasing when the derivative is positive. That looks like 0 to 2, 4 to 6, and then also from 8 to 9, because it told us the interval goes all the way to 9. And it's decreasing when the derivative is negative. And there we go. Okay, and I'm going to write that just so you know what we did. The derivative's positive, derivative is negative. Part B. On what intervals is f prime of x greater than 0? Well, I just answered that, so I'm going to write that there. See those. Okay, good. We got that one. How about part C? At what values of x does f have a local max or min? Justify. So f is going to have a local or relative minimum when f prime changes from negative to positive. So it looks like here, negative to positive, negative to positive. So f has a relative min at x equals 4 and x equals 8, since f prime changes from negative to positive. F has a relative max at x equals 2, actually, and sneaky one there, x equals 6, since f prime changes from positive to negative. So this time positive, negative, kind of sneaky one, but we got it. Let me erase that. All right, letter D. On what intervals is f concave up or down? All right, f is concave up like a cup. I would say from, well, maybe what? Let's say 3 to 6. Concave up like a cup. And so you would think it's 3 to 5, but it's not. It's 3 to 6. F has F is concave up like a cup when the derivative is positive. So that's why I picked those values. And not the derivative. The slope is positive. Okay, the slope is positive here. The slope of the first derivative is positive. So it's going to also be concave up from 6 to 9. F is concave down like a frown when the first derivative is negative. So the first or not negative, decreasing. I got to be careful with my words here. The first derivative is decreasing from 0 to 3. So that means that the second derivative would be negative, which implies that it's concave down like a frown on that interval. 0 to 3. Okay, so E, state the x-coordinate of the point of inflection. Well, it looks like we changed from concave up to concave down at x equals 3. So we got an inflection point at x equals 3. And we can justify it by saying since f double prime, okay, the slopes of the first derivative function changes from negative to positive. And G, we have, if possible, determine the x value at which f attains its max or min. All right, maybe it would help us to sketch this graph now. And we could kind of get an idea. Oh, I forgot part F. I went from E to G. There we go. That would help me answer my question. All right, so part F says, assuming that f of 0 equals 0, we have this. Sketch a graph. So from 0 to 2, I'm increasing, and I'm concave down like a frown. So maybe it would look something like this. Okay, I'm still concave down like a frown until 3, but I'm going to start decreasing. So I'm kind of nice, smooth graph. Okay, now from 2 to 4, I'm decreasing, but from 3 to 6, I'm concave up like a cup. So I'm going to kind of turn that frown upside down this way. I'm going to start increasing from 4 to 6, and I'm concave up like a cup. We're not quite sure how high it goes. Maybe it goes up here, who knows? Okay, and then from 6 to 8, I'm decreasing, and I'm concave up again. So it's going to look something like this. And I'm going to start increasing, and I'm going to still be concave up like a cup. So this is a possible graph, okay? We don't know exactly how high it goes or anything else. So now, if we look at Concavity, it's a little bit easier. We have a possible min. We can't tell exactly. At x equals 0. Oh, it looks like it on our graph, but it might not be. We're going to have possible maximum value at, let's see, it could be at x equals 2. It could be x equals 6. It could also be our endpoint, x equals 9. We don't know how high that goes up. All right, so there was a lot going on there. So I would like you to try example 7, part A, or part 1, and just put letters C and E in your whisk. There you go.